Since its invention in the 17th century, the light microscope has become an essential tool for biologists. From the first microscope to the state-of-the-art super-resolution techniques available now, biologists have been able to observe and study different cellular components and processes in vivo. Today, it is even possible to image single molecules or to follow dynamic cellular processes. Optical tweezers or optical traps were conceived in the late 80s and are now used as a complementary technique to light microscopy for the non-contact, precise manipulation of the microscopic samples under observation. It is essentially a powerful laser beam which is highly focused by the microscope objective lens. The laser is able to exert forces on microscopic particles to accelerate and trap them close to the laser focus, which is called the optical trap. For the manipulation of biological samples, a near-infrared, non-visible laser is commonly used to minimize optical damage. It is easy to explain how optical tweezers work by means of ray optics. The incoming rays change their direction when interacting with the particle and therefore change their linear momentum. By Newton's laws, the change in momentum is transferred to the particle in terms of a force. If we consider all rays, we can see that the particle is stably trapped close to the laser focus, as long as the incoming beam has a high numerical aperture. A single laser gives rise to a single optical trap. However, by controlling light propagation by means of holographic techniques, for example, we can generate arbitrary trap patterns and exotic beams with special properties. This way, it is possible to trap multiple particles in 3 dimensions at the same time, grab a large object from several sides, or rotate a sample. Optical tweezers allow the complex manipulation of particles and, very interesting, are also a quantitative tool to measure the forces exerted on the trapped samples. They have lots of applications in various fields. In microfluidics and micromechanics, they are used to sort particles or build micromotors. In physics, to study colloidal systems, or in nanotechnology to build nanometer particles such as carbon nanotubes. The main applications are found in biology, where optical tweezers have been employed to manipulate from cells down to cells' internal organelles, bacteria, viruses, or even single molecules. They have allowed selective cell culture, tracking of intracellular organelles, the study of mechanical properties of cellular membranes, the DNA or molecular motors, responsible for intracellular cargo transport. Intracellular transport plays an essential role in cell function and is therefore critically related to many diseases, ranging from neurodegeneration to cancer. The impact of the research done using optical tweezers is extraordinary, and we expect it to be increasingly important in the future, as the technology improves and biologists are able to process and understand the new data. This data provides additional information on the mechanical properties of the processes under study and should facilitate a better understanding of cell behavior.